We talked in the previous video a little bit about naming carboxylic acids, and we talked about what a carboxylic acid looked like. It was a carbon double bonded to an oxygen, so that famous carbonyl group, and that was attached to an OH. Now, conceptually, you want to think of that OH as a potential leaving group. All you have to do is protonate that, and it can pop off of that molecule. Now, the actual mechanics of that are a little bit more involved, but in general, in your mind, you want to think of that other group as a leaving group. And so if that can leave, you can do the same types of reactions as you learned about in Organic Chemistry 1 that involved leaving groups. You could do substitution reactions. All you need for a substitution reaction is a nucleophile and a leaving group, and the nucleophile takes the place or substitutes itself for the leaving group. Well, if we have a leaving group here, then we can start substituting that OH with other things. And those other things create what are called carboxylic acid derivatives. And they're derivatives because you would make them from these carboxylic acids. Carboxylic acids are really common. All you need is charcoal, maybe some oxygen or water, and then you're done. That's all you need to make this functional group. All of those are really common on Earth. And so you tend to have a lot of carboxylic acids. They're everywhere in living things, fatty acids, amino acids, etc. And so you can use those to make these other derivatives by replacing the OH with a different thing. Now, as we introduce these other things, you want to conceptualize them in your mind as also being just different leaving groups. So you can interchange each of these different things. Well, let's start with the leaving group that was most prevalent in Organic Chemistry 1. That was the halogens. The halogens are big. You have fluorine, chlorine, bromine, and iodine. Fluorine is the exception. It's actually pretty small. It's the size of a hydrogen atom, which is the smallest atom on the periodic table. But the others, and which is why we don't see fluorine very often, you would remember that we really only saw it when we talked about crown ethers, because the crown ether was able to stabilize a cation that was connected to the fluorine and sort of lure it away, forcing the fluorine to be by itself. But aside from, if you don't have crown ethers to work with, then you don't really deal with fluorine that much. Otherwise, the next smallest one is chlorine. Chlorine is the size of a methyl group. Think of that, 4 atoms, carbon and 3 hydrogens. Chlorine is the size of all of them put together. And then bromine is even bigger than that, iodine is even bigger than that. The fact that they're so big made them amazing leaving groups because it meant that they could take the electrons with them, have a negative charge, and spread it out or dilute it over their huge space, and that stabilized that negative charge. So the halogens were awesome leaving groups. The way that they symbolize halogens in general is with a capital X. So kind of like a capital R is any carbon chain, a capital X in organic chemistry is any halogen. So usually that means chlorine, bromine, or iodine. Okay, so these carboxylic acid derivatives that have halogens in them are called acid halides. The acid is referring back to the fact that they're derivatives of carboxylic acids, and you have a halogen attached, so halides, acid halides. The suffix for acid halides, if you have an acid halide, is oil, and then I'm going to give the general term halide. Now you would never use the name halide. You would use the first syllable of whatever halogen you have. So for example, that could be brome, the first syllable of bromine, and IDE. So you could have oil bromide, or it could be chlor if you have a chlorine. Chlor is the first syllable of chlorine, add the IDE, you'd have oil chloride. So the hal in halogen is replaced by the first syllable of whatever halogen you have. Okay, so here, in this first one, we have a carbon, and notice that the similar thing happens here as we saw in carboxylic acids. The functional group itself, the carbon in it, has 3 bonds taken already by the functional group. So this is always going to be at the end of a carbon chain. Now we saw in the previous video how there's a table that lists the different priorities of these different functional groups. And you can see that acid halides are pretty high on that. The highest one are carboxylic acids. Esters are technically more important, the second most important, but acid chlorides are the third. So usually if an acid chloride is on a molecule, it'll be carbon number 1. The only thing that could beat it out are carboxylic acids and esters. Well, we don't have either carboxylic acids or esters here, and so this carbon that has the carbonyl on it will be carbon number 1, and then 2 and 3. Here we don't have any branches, so that's nice. 3 carbons in the backbone, prefix is prop. Now, in the acid halide, the acid halide, which will be represented in the suffix, includes the double bond to the oxygen and the single bond to the bromine. So that'll be represented in the suffix, which means we don't need it represented in the infix. The infix will represent all the other bonds. Those are all single bonds. So the infix will be AN, remember. If you have all single bonds, the infix is AN. If you have at least one double bond, it's EN. If you have at least one triple bond, it's YN. And those are following the vowels, A, E, and I. First 3 vowels. I got changed to a Y over time. So you have propan. Now for the suffix. We see that we have an acid halide. Specifically, we have an acid bromide. So the suffix will be oil, and then first syllable of the halogen, brom, and the ending ide. So the full name for this compound will be propanoyl bromide. All right, next one down. We see that we only have one functional group here. We want to give the lowest number to that functional group, so we make the carbonyl carbon number 1. And we have 1, 2, 3, 4 is the longest carbon chain I can have. I'm going to circle that backbone so that it stands out from the branches. 4 carbons, the prefix for that is bute. Oh, and also notice with these propanoyl bromides, we didn't have to give a number for where this is because it's always at the end of a chain. So here it's at number 1, it's implied because it's the only functional group here, and it's is at the end of the chain. So we don't have to give a number to say where the acid halide is attached. So you have 4 carbons, so bute. If you look at now we have the acid halide, in this case the acid chloride here, and that's usually the most common one, is the acid chlorides. That's going to be represented in the suffix. So the other bonds are the ones that will be represented in the infix. Those are all single bonds, so the infix here will be AN. So butan, and then we have an acid chloride. So oil, because we have a chlorine, the first syllable of the chlorine, chlor, and then IDE. So the name for this backbone will be butanoyl chloride. We do have a branch. The branch is coming off of carbon number 2. Always between numbers and letters goes a dash. In that branch, there is only 1 carbon. And the prefix for 1 carbon is meth. Because it's a carbon branch, immediately after that prefix comes YL. So you take that branch name and put it in front of the backbone name, and the full name that you'd have would be 2-methyl butanoyl chloride. So the naming for these is really similar. You have all the different kinks and possibilities as you have in general with naming, having different branches, maybe having a chiral center, etc. And if they want you to name a chiral center, they'll give you the 3-dimensional configuration of the bond. But the new thing here is having this new functional group, these acid halides. And so the one difference that you want to emphasize, you want to take away from this video, is that you have this oil halide. It could be oil bromide, oil chloride, oil iodide, but the oil halide suffix goes with these acid halides.